Hi, everybody. Let's move on to lecture number 3, thermal analysis. For the last lecture, I introduced about the thermal resistant network and how to find your junction temperature for more complicated system, and I left with the chip carrier. For this lecture, we're going to talk about our general equations governing conduction, and based on page number 315, topic 8.3.2. Let's take a look at three-dimensional thermal equation from equation 8.27. That's the del square T equal to 1 over alpha partial derivative for the temperature with respect to time minus Qi over K, and you know Qi is the heat rate per unit volume in the unit of watt per cubic meter. K is the thermal conductivity, and your alpha is the thermal diffusivity in the unit of meter square over second, or that's equal to Kc rho, and that's rho is the density of mass, the mass density in the unit of a kilogram per cubic meter. Del square simply is the Laplace operator. That's the partial derivative, or the second partial derivative of the temperature with respect to x squared plus the second partial derivative of the temperature with respect to y, and so on. For the special case, we're going to solve the equation, looking for the temperature in the term of time. For no internal heat, you have no Qi, or Qi is equal to 0. So the equation 8.27 drop down to equation 8.29 from the book, and in that case you can solve for the temperature depend on the time. For the second one, stable temperature, that your temperature doesn't change with time. So from equation 2.87, this term drop, you have only negative Qi over K. That's equation 8.30. And also in combination, if your temperature is constant or not varies with time, and you have no heat source, Qi equal to 0, you end up with the equation 8.31. That's the del square T equal to 0. Okay, let's just leave it like that, just to get idea. Nothing else. Now let's move to topic 8.3.3, heat flow in cylindrical packages. Let's consider when you have no heat source, that means your Qi equal to 0, and from the heat equation 8.23a, your Q is negative Ka, and derivative of temperature with respect to x, that's one dimension rate. You don't have the term x, y, and z. And now let's simplify the equation. For the cylinder, take a look at the figure here. The cross-section area, you determine the heat flow along the length of the cylinder. You have the cross-section area to be 2 pi RL, where R is the radius of the cylinder. It's the arbitrary radius. And you replace X by R, you end up with this equation, and so for T, or the temperature different, T1 and T2, along the cylinder. You have delta T equal to Q over 2 pi KL Ln R2 over R1. By comparing the equation, or the thermal equation, delta T equal to QRT, you end up with RT of the cylinder, or thermal resistance of the cylinder, to be Ln R2 over R1, and divided by the product of 2 pi KL. That's equation 8.24. Now you know for the cylinder, that's not in the shape of rectangular as we start with before. Your RT become Ln over R2 over R1, where R2 is the outer radius and R1 is the inner radius of the cylinder, and K is their thermal conductivity. L is the length of the cylinder, where if you have the thermal conductor in rectangular shape, you know that your RT is equal to L over Ka, right? Now let's consider the heat flow through layer composites. In this case, you have different type of materials sandwiched together. Okay, the heat flowing transfer from the left to the right. So you have Q in, you have Q out. Of course, you Q out equal to Q in, and you can write your thermal resistance network. They are all in series. Okay, you have RT1, you have RT2, RT3, and RT4, and of course you have a different junction temperatures. And then you have Q flowing through, the circuit, the thermal circuit. Let's keep in mind your RT equal to L over Ka. So the heat will flow from higher temperature to the lower one. So that means that the heat flow from T1 to T0. T0 is the ambient temperature or the room temperature. Apply your thermal equation delta T equal to your RT. Okay, and you add them up together. You have simply T12 cancel out to negative T12 cancel out to T12. So you end up with T1 minus T0 equal to Q multiplied by the total thermal resistance. You just add up each thermal resistance because they are all in series. Now let's introduce heat transfer by convection. You will have a new equation. For thermal resistance, if the heat transfer by convection, your T equal to 1 over HA, not equal to L over Ka anymore, where H is the conduction coefficient in the term of in the unit of watt per meter squared degree Celsius. Okay, in this case, you have the heat transferred from the left to the right through the air layer, and you have heat transferred by conduction, and then out of the system through the boundary layer, and that's the air or fluid. So you have three resistor, thermal resistor, connected in series. You have RT1, RT2, and RT3, where RT1 is the heat transfer by convection, as well as the RT3. But RT2 is the heat transfer by conduction. We do the same thing. You set up equation. From the left, you have Ti minus T1. That's the heat transfer by convection. So you put Q over HIA instead of L over Ka. But for T1s minus T2, that the temperature different. This is the heat transfer by conduction. So you put QL over Ka. T2 to T3, that's the convection. Yet, three equations together, you end up with Ti minus T3. That's equal to Q multiplied by RT total, or total thermal resistance, both by conduction and convection. Very simple. Okay, to get more understanding, let's take a look at the problem 8.15 of chapter 8. An aluminum cylinder is used to contain a thyrothon that dissipates 800 watts. The cylinder has an inside and outside diameter of 2.6 and 2.8 inch, respectively, and a length of 4 inch. That's the cylinder. Okay, please keep in mind, it's not a rectangular. Determine the thermal resistance of the cylinder and the temperature difference delta T. Okay, first of all, what is the thyrothon? You probably heard about it, some of you. It's some kind of a high power electrical switch. Now we will focus on the aluminum cylinder. That's the material we are talking about. From equation 8.34, because this is the cylinder, so your RT equal to Ln of R2 over R1 divided by 2 pi KL. From the table 8.3, page 316 of my book, your K aluminum is 126 watt per meter degree Celsius, and L is given, right? 4 inches. You convert inch to meter. You end up with 0.1 meter. So your delta T equal to QRT. That's the 0.75 degrees Celsius. So that's the temperature difference. Problem 8.16, topic 8.3.4. Determine the heat transfer across the plate. Divided in figure 8.11 if the dimensions are 8 millimeter by 0.5 meter by 0.6 meter. The plate is made from aluminum 2004, just by coincidence. This year is the 2024 rate. Given the convection coefficient H is equal to 6 watt per meter degree Celsius on one side of the plate and 3 watt per meter degree Celsius on the other. The temperature is different. The temperature difference is 20 degrees Celsius. Examine the three components of the thermal resistance and discuss the factor limiting the amount of heat being transferred across the plate. Okay. For the thermal conductivity of aluminum 2024, from table 8.3, page number 316, that's the 121 watt per meter degree Celsius. And thermal resistance are connected in series. You have T1, the temperature difference, or T2 minus T1, that's 20 degrees Celsius for the outer system and the innermost system. And then you have the T equal to QRT. So just work out for thermal resistance for each element. The first one is by the heat transfer by convection. You put 1 over HA. 2, that's the heat transfer by conduction, and R3, heat transfer by convection. It's just not plug in work out on the number equation, but you have just take a note on the number of each RT. You can see that this one is very small because it's talking about aluminum ring. They have a good thermal conductivity. So you have very small RT compared to RT1, that's the heat transfer by convection, and RT3, convection, heat transfer by convection as well. So that you limit the amount of heat to transfer from the innermost system to the outermost system. That's the 0.131. Okay, I believe. Thinking about breaking the lecture into two parts. This may be too long. Let's see if I continue. Just one more page. It's better to break this lecture into series 2. Okay, so that's all, for lecture number 3, series 1.